Applying mathematics in biology, the importance of the Hardy-Weinberg principle. Hardy-Weinberg, why we need math in biology. Does it really take a village to raise a baby? I don't have kids myself, but various single parents, happy couples, and weird uncles make it look easy on TV without even leaving the house. So, it stands to reason you also don't need a whole village to tell if a baby is genetically significant, right? That is right, but it's because you actually need infinite villages. From the triviality of eye color to the weightiness of cystic fibrosis, our genetic makeup is our first step towards individuality. If we want to know how together or alone we are in our mishmashes of Punnett squares, we must look beyond ourselves for the sake of us all. That is where today's topic, the Hardy-Weinberg principle, comes in. My name is Justin Fowle. I'm not a medical expert, a genetic scholar, or even a particularly good biology student. At time of recording, I have a low B. However, I have two things going for me that make me well suited to explain today's topic. One, I used to be a baby, and two, I love a shortcut. All of this leads me to my thesis statement. The Hardy-Weinberg principle is the non-negotiable starting point for all genetics-related medical research. To show you what I mean, I will first explain what the Hardy-Weinberg principle is in the simplest terms I can. Then, with that knowledge, I will demonstrate how integral the Hardy-Weinberg principle is in determining the viability of research in the areas of general genetics and specific diseases. And finally, I will briefly touch on non-medical applications of the HWP and the importance of math in general to the study of biology, per the assigned topic. Let's start with a very brief look at the namesakes. In 1908, an English mathematician named Godfrey Harold Hardy and a German doctor for the poor named Wilhelm Weinberg independently arrived at what is now known as the Hardy-Weinberg principle. The Hardy-Weinberg principle states that three genotypes will either achieve equilibrium from two alleles generation after generation, or some outside force will make the equilibrium unachievable. If the distribution falls outside of the Hardy-Weinberg equilibrium, further investigation is warranted. You find that distribution by using this equation, courtesy of the amoeba sisters, and the outside forces I've mentioned are these five here. We'll now look at both in depth. The HWP checks if something is happening more or less often than we'd expect from generation to generation by measuring actual occurrences of genotypes against what we'd expect based on the equation from the previous slide. As an example, here's that earlier Punnett square from Jankowska et al. The dominant allele and the recessive allele are both 50% likely in this example. U square 50% for the dominant, capital A in the square and lowercase p in the equation, and the recessive, lowercase a in the square and lowercase q in the equation on each side to get 0.5. It's 0.25 plus 0.25 equals 0.5. Then, as shown in the middle of the equation, you multiply the dominant and recessive, then multiply that by 2 to get the other 0.5, which adds up to 1. You then can see how this looks on a graph thanks to this crude mock-up from 2009 made by Malik. This is, of course, a simple example where equilibrium is achieved. But what about those outside forces? Remember those infinite villages I mentioned at the beginning? That infinite population is just one of the 5 assumptions that are assumed in calculating the Hardy-Weinberg equilibrium. You must also assume a total lack of natural selection, mutation, and migration, along with random selection among mates, as shown here in another still from an Amoeba Sisters video. If these assumptions are not in place, you can end up with genotypes existing in proportions that contradict the frequency of the two alleles. Obviously, real life breaks all these assumptions every day, which is why the HWP is a shortcut, not an absolute truth. This shortcutting functionality is what makes the HWP so useful to medical and genetic researchers. Without the HWP, it would take longer to quantify if something was amiss. The HWP provides a rough idea of what to expect from a sample. If the equilibrium is not represented in the data you are studying, it may be time to investigate which, if any, of the assumptions are being violated. If the equilibrium is approximately represented, you might switch your focus from hereditary factors to environmental ones. Before we dive into a specific real example, here's a hypothetical for you. Would you want to buy bread from a baker who didn't know how frequently imperfect loaves were being baked? While it may not hurt you to eat a slightly doughy peanut butter sandwich or some toast that was burned before you even put it in the toaster, that baker is never going to improve if they don't collect your feedback and establish some benchmark of acceptability because they won't know anything is wrong in the first place. It's not a perfect analogy to the Hardy-Weinberg principle since you definitely know something was wrong in most of the following examples, but the HWP serves as that first shared link. In a moment, I will go over an example of the Hardy-Weinberg equilibrium not being achieved because of a broken assumption relating to sickle cell anemia. Before I do, I should also note that HIV was mentioned in the same paper as sickle cell. A 2008 retrospective on the HWP from Mayo explained how Weinberg incorporated the HWP into his work studying twins, and a 2015 meta-analysis from Namapashaki et al. Includes works on Alzheimer's and lung cancer. All these distinct concepts begin with a comparison to the Hardy-Weinberg equilibrium. To drive home that point even further, that meta-analysis was actually a piece laying out an argument for how the HWP was used incorrectly, without sufficient data, or not at all in the work studied. While not encouraging for the studies in question, that does mean that not only is the HWP used to investigate important medical subjects, but it is considered important enough to then be double-checked by the academic community. Moving on, here's the sickle cell anemia example from How to Teach the Hardy-Weinberg Principle, a 2018 piece by Professor Michael J. Wise. Wise demonstrates how those with the homozygous genotype of s, sickle cell carriers with both recessive alleles, are underrepresented compared to heterozygous S, carriers. In this case, natural selection is violating the HWP, as the s individuals are more likely to die of malaria before reproducing, resulting in fewer s individuals and more s individuals than you'd expect if no assumptions were violated. As you can see, homozygous S individuals are also underrepresented, which I was not able to grasp. Regardless, you can see how the s carriers math doesn't add up. With a squared allele frequency of 0.1139, you'd expect roughly 23 individuals in a sample of 200, yet only 10 are observed, which is our cue to take a closer look at sickle cell or whatever else may result in such skewed quantities. As a side note, in my research I came across many pieces like Rolfson-Weir's 2008 assessment of how to calculate specific Hardy-Weinberg figures, suggesting that a small number of genotypes would be better served by using an exact test for p-values. This doesn't invalidate Hardy-Weinberg's importance, but it does show that it can be improved upon, partially due to improvements in technology. If you remember calculating p-values by hand before the teacher let you use a calculator or the tables in the appendix, you understand why exact tests might not have been all the rage in the early 1900s. Casting such a wide net with HIV, Alzheimer's, etc., you cannot overstate the importance of the HWP to the study of human health. In that, the HWP serves as the nth example that math is important to biology, though I'd argue that is self-evident. And finally, the HWP's importance is bolstered once more by its use in non-human studies. In my research on the HWP, I did not find any general connections or arguments regarding the HWP's existence proving the need for math and biology because, like I said, that seems a bit obvious and broad. Nevertheless, that was part of the topic I chose, so I will provide a couple examples on the matter with a bonus look at the HWP in a non-human context. Let's start with an extremely obvious example of why math is necessary in biology. Think back to all the labs we've done so far. Imagine the headache you'd have trying to figure out how much water to put in a mug if Dr. Hempel had just said, some water. Furthermore, we have worked with dangerous substances, so if we had only been told to use a little instead of a numerical measure, this might be my funeral instead of my presentation. That is, of course, an unrealistic example, but you get the point. However, there's another example from earlier in this course that is less obvious. The Yellowstone wolves. Everything Science's 2020 video on the matter stated the exact number of wolves that were reintroduced, 14. While the video does not explain the calculations made to arrive at that number, it's safe to say it wasn't a lucky guess. And speaking of conservation, that is one area of study I found that wasn't strictly human-based for applications of the HWP, though it took a while to find. After over 20 pages of results on the Hardy-Weinberg and Hardy-Weinberg application turned up only medical applications or overviews, studies, retrospectives, etc. on the HWP itself, I tried Hardy-Weinberg color, hoping to find something on eye color, hair color, color of peas, or something along those lines. Instead, I found Hep et al.'s 2012 research on wool color variation amongst Brazilian Creole sheep. From A to F, we have white, black, Creole, dark gray, and 2 photos of light gray. Granted, the HWP is only mentioned twice, but the researchers ended their conclusion by emphasizing the need for random mating to keep the variety of wool colors bountiful, which aligns with the random mating assumption of the HWP. On the subject of assumptions, in a 2007 study from Short et al., the population assumption was deemed broken to the point of potentially rendering data unusable when studying dogs as a whole. However, restricting the populations to be within single breeds resulted in a far greater chance of compliance with the assumption. So, if you want to know if all dogs go to heaven, you should first figure out if all Great Danes go to heaven. As you can now see, even if just in passing, the HWP still asserts itself as a genetic cornerstone to research, medical or not, to a degree of import that rivals the crucial bond between any and all mathematics and biology. Over a century after its creation, the Hardy-Weinberg principle remains undeniably foundational. The product of a mathematician and a doctor, its simplicity allows complex problems to be addressed at that very specific crossroads of math and medicine. It does so by providing a point of comparison at the beginning of the research process, serving as a shortcut to potential explanations. And in doing so, it has since reached beyond its initial and most noble use to both inform other research areas and highlight the connection between arithmetic and biology. Despite its reliance on assumptions, it is a concrete, unmovable part of the research of what makes us and what ails us. So, as we continue to try to understand ourselves and our health and better our existence, we must first do the math. Thank you.